Hi guys, I am Krishna Teja, one of the faculty at Gate Pathshala. Let's solve aircraft structures questions from Gate 2026. Let's solve question number 16 from Gate 2026. So it's given number of independent elastic constants that a fully anisotropic linear elastic material can have is, they're giving you the four options 36, 21, 10 and 2. Let's see how to solve this. So for solving this, you should have the basic idea of elasticity. So since they are talking about linear elastic material, stress is directly proportional to the strain. Now you can say stress is 3 by 3 matrix. So if you relate the stress and strain, you will get a stiffness matrix. This stiffness matrix contains 81 constants. By applying complementary shear stress, this can be reduced to 54 constants. Then by applying complementary shear strain, we get into 36 constants. Then by applying strain energy, this can be reduced to 21 constants, and these 21 constants are independent elastic constants. And the material is called anisotropic material. So the correct option is option B. So let's solve question number 17. A cantilever beam with a unsymmetric cross section is subjected to a transverse shear force P at its free end. P acts at the shear center of the beam cross section. Which one of the following statements is true about the deformation of this beam? They are giving you the four options. Option A, the beam undergoes only torsion. Option B, the beam undergoes only bending. And option C, the beam undergoes both torsion and bending. And the beam undergoes neither torsion nor bending. Let's solve question number 17. So since they are talking about the cantilever beam, let's take a cantilever beam of some arbitrary cross section. And since it is arbitrary cross section and that, so it's fixed cantilever beam. So since they are talking about the unsymmetric cross section, and assume that this is the location of shear center, and apply a load exactly through the shear center. So if you know the basic idea of the shear center, so it is the point on the cross section where the beam undergoes only bending and there won't be any twisting. So you can say there is no twist, only bending is possible when the load is applied at shear center. So option B is correct. Let's solve question number 26. The state of stress at a point in a 2D body in the XY Cartesian coordinate system is represented in matrix form as sigma. The transformation matrix Q rotates the coordinate system to a new x dash y dash Cartesian coordinate system. Select the correct options that represents the state of stress in the new coordinate system, and they are giving you the 4 options. The given options are this. Let's start with what is the sigma and what is q. So let's draw the plane x and y. Now you have to transform this state of stress to a new coordinate system, let's say x dash and y dash. Let's say this is making an angle theta with the x plane. So to understand, first in a 2D state of stress, let's say sigma is equal to sigma xx, tau xy, and sigma yy. So this state of stress we know from the stress transformation. Now you have to shift this coordinate system to a new coordinate system of x dash y dash. For that we require a transformation matrix. So from this you can write x dash is equal to x cos theta plus y sin theta. Similarly, from here you can write y dash is equal to, so you can write it as minus x sin theta plus y cos theta. So now you have to represent this in the matrix form. So you can write it as x dash y dash is equal to cos theta, then you have sin theta, then you have minus sin theta, then you have cos theta, then you have x and y. So this is what is called Q, the transformation matrix. So for any state of stress given in a 2D plane, if you want to transfer that to a new coordinate system, first you should know that sigma x dash can be written as sigma xx plus sigma yy by 2 plus sigma xx minus sigma yy by 2 cos 2 theta plus tau xy sin 2 theta. And similarly, if you want, sigma y dash is sigma xx plus sigma yy by 2 minus sigma xx minus sigma yy by 2 cos 2 theta minus tau xy sin 2 theta. So for shear stress in the new coordinate system, tau x dash y dash is equal to sigma yy minus sigma xx by 2 into sin 2 theta plus tau xy cos 2 theta. So you should know this transformation from the basic stress transformations. So we'll check the options using the 3 formulas. Let's take the option A. We know that the transformation matrix Q is equal to cos theta, sin theta, minus sin theta and cos theta. So the first option is transformation matrix into the stress matrix, then they are saying transpose of the transformation matrix. Now if you substitute cos theta, sin theta, minus sin theta, then cos theta, then we know that the transformation matrix is sigma xx, tau xy and sigma yy. This is the stress matrix. Then transpose of transformation matrix will be cos theta minus sin theta, then you have sin theta, then cos theta. So this will give us the new state of stress, that is sigma x dash, then tau x dash y dash, then tau x dash y dash, then you have sigma y dash y dash. Now to get this sigma x dash, now multiply these two first to get, so this can be written as sigma xx cos theta plus tau xy sin theta, then minus sigma xx sin theta plus tau xy cos theta, then the second row with the first column, then tau xy cos theta plus sigma yy sin theta, then tau xy minus tau xy sin theta plus sigma yy cos theta. So once you attain this matrix, then you have to multiply with this cos theta sin theta minus sin theta cos theta, then you'll get sigma xx cos square theta plus tau xy cos theta sin theta plus tau xy cos theta sin theta plus sigma yy sin square theta. Then for the second element, minus sigma xx cos theta sin theta plus tau xy cos square theta, sorry, minus tau xy sin square theta sigma yy cos square, sorry, cos theta sin, and minus sigma xx cos theta sin theta plus minus tau xy sin square theta plus tau xy cos square theta plus sigma yy cos theta sin theta. Then sigma xx sin square theta minus tau xy cos theta sin theta minus tau xy cos theta sin theta plus sigma yy cos square theta. So the transformed matrix sigma x dash, tau x dash y dash, and tau x dash y dash, then sigma y dash y dash. Now compare first row first element with the matrix you got. So from this we can get sigma x dash as sigma xx cos square theta plus, so here you can see it's both are same, you can write it as 2 times of tau xy cos theta sin theta plus sigma yy sin square theta. Now using the basic trigonometry, you can write cos square theta as 1 plus cos 2 theta by 2, then sin square theta is 1 minus cos 2 theta by 2. Now by substituting that, you will get sigma xx plus sigma yy by 2 plus sigma xx minus sigma yy by 2 cos 2 theta plus, so this can be written as tau xy. So 2 cos theta sin theta can be written as sin 2 theta. So this is your new normal stress on the transformed plane. If you see from the transformed matrix, these two elements are equal. You can write directly tau x dash y dash as sigma yy minus sigma xx by 2 into sin 2 theta plus tau xy cos 2 theta. So again you can use the basic trigonometry to get this relation. Then from the last element, you can get sigma y dash as sigma xx plus sigma yy by 2 plus sigma xx minus sigma yy by 2 cos 2 theta plus tau xy sin 2 theta. Sorry, this should be minus. Now using these three equations, you can say transformation matrix into the stress matrix into transpose of the transformation matrix gives you the correct transformed matrix, that is sigma prime. Okay, once if you are getting this option, then using the matrices, you can say Q transpose is equal to Q inverse from the orthogonal matrix If you see option B, it's nothing but they are just changed the option. Option A is correct, then option B is also correct. Then if you see the option C, so Q inverse, you can write it as Q inverse is nothing but the Q transpose, then Q transpose of transpose will give you Q. It's nothing but option A, then option C is also correct, then option D is wrong. So the correct options are A, B and C. Let's solve question number 40. Consider a unit square body as shown in the figure below. The body is subjected to the deformation field U is equal to minus AY and V is equal to AX, where A is a constant. Due to the application of this deformation field, the body undergoes, so they are giving you the four options. Option A, biaxial deformation, option B, pure shear, option C, pure bending, and option D, rigid body rotation. Let's see how to solve this question. Let's start with option A. Since they are talking about the deformation, we know that from the basic elasticity, strain in the x direction can be written as dou u by dou x. So if you substitute the displacement field or the deformation field, they are giving, you will get strain in the x direction is equal to 0. Similarly, strain in the y direction can be written as dou v by dou y. Since v is also independent of y, you will get 0. So from these two, you can say no deformation. Okay, option A is wrong. There is no axial deformation in both the directions. Then when it comes to pure shear, so engineering shear strain gamma xy, that is equal to dou v by dou x plus dou u by dou y. Now let's substitute the given deformation field. So dou v by dou x will be equal to A, and dou u by dou y is minus A. This will come out to be 0. So no shear. So option B is also wrong. So from the basic elasticity, know that stress is directly proportional to strain. Since there is no normal strain and shear strain, there won't be any stress. Sigma is equal to 0 and no bending. Okay, option C is also wrong. Now let's go to option D. It's rigid body rotation. We know that gamma z or gamma xy is equal to half into dou v by dou x minus dou u by dou y. Then again substitute the given deformation field, half into dou v by dou x will yield you A minus of, then dou v by dou u by dou y will be minus A. This comes out to be 2A by 2, then omega z is equal to A. So we have a constant rotation. So the body undergoes rigid body rotation. So option D is correct. Let's solve question number 16. Given Young's modulus 200 gigapascal, and they are giving the lengths of the stripped cantilever beam, and it has different moment of inertias. One is with I2, and both bars are made of the same material. They are asking to find deflection at point A. So to solve this question, we have different techniques. So one is the double integration method. Then you can use a strain energy method, or you can go for a moment area method. So let's try to solve this question using the moment area method. So if you want to solve this question using the moment area method, first thing you should be knowing about what is moment area method. Then in that, basically it is given by Moore. So Moore's theorem 1 and Moore's theorem 2. Since they are asking the deflection, you can go for Moore's theorem 2. Now Moore's theorem 2 says that area under the bending moment diagram into the centroidal distance from the point where you have to find the deflection will give you the deflection at the point. Okay, and regarding to that, you have to divide the area under the bending moment diagram with the flexural rigidity. Flexural rigidity means it's the parameter when you multiply Young's modulus with the moment of inertia. So let's see how to do this. So first try to draw the bending moment diagram. So for that, we have to calculate. We know that since it is a cantilever beam, so there won't be any bending moment at point A. It will be 0. At point B, it is just P into L1, and at point C, it is P into L1 plus L2. So for that, since we know the bending moment at point C, it is P into L1 plus L2, and at point B, it is P into L1, and there is no load acting on the beam apart from point A. The shear force diagram is just a straight line, and the bending moment diagram will be an inclined line, something like this. So since they are asking to find the deflection at point A, and this is point B, and this point C, so this of the length L1. So you should mark the lengths very carefully. Okay, if you miss one part, whole solution will go wrong. So let's see how to do this. So we have to find deflection at point A. So first, since it is a triangle, and we know that for the triangle, the centroid will be located at a distance of 2L by 3 from this end. Okay, so this is 2L1 by 3. Okay, first you should mark the centroids from point A to the whole cross section perfectly. Then let's write the area of that. So half into base is L1, and the height is P into L1 divided by Young's modulus is same for both the beam, and it has moment of inertia of I1. I mean for this part of the section. Okay, into the centroidal distance is 2L1 by 3. Okay, once you are done with this one, then since it is a trapezoid, you can break this as a rectangle and a triangle. Okay, first we'll go with the rectangle. So first you mark the centroid of the rectangle, which is located from point A to this centroid of the rectangle. This will be L2 by 2 of the rectangle. It is P into L1 into, and the base is L2 divided by, now since it is made of the same material and it has different moment of inertia, so you just write divided by E into I2, then the centroidal distance will be L1 plus L2 by 2. So this whole distance is L1, so from point B it is located at a distance of L2 by 2. Okay, plus, so this part is P into L1, so this will be P into L2. Okay, now you write, first you mark the centroid of the triangle. Okay, now this will be at a distance of L1 plus this distance, so this distance will be 2L2 by 3. Okay, so it will be half into, so height is PL2 into base is L2 divided by E into I2, and the centroidal distance will be L1 plus 2L2 by 3. Now you solve this, delta A will be equal to, so you can cancel this and this, so you can take P common, then Young's modulus also into, so this will be L1 cube by 3 plus L1 into L2 divided by I2 into L1 plus L2 by 2 plus you have L2 square divided by I2 into L1 plus 2 L2 by 3. So P is given, Young's modulus is also given, L1 and L2 is also given. Then you have, sorry I missed I1 here, so I1 and I2 is also given. So you just solve this equation by substituting the lengths and the moment of inertia and the Young's modulus also. You will end up with 0.9 millimeter. Let's solve question number 58. So this is the given data. The ultimate stress is 200 megapascal and the mean radius is 0.2 meter and the thickness of the wall of the tube is 0.04 millimeter, and they are asking to find what is the torque, okay, it can sustain based on this. So they are giving you a thin wall tube of radius 0.2 meters and the thickness of the tube is 0.004 meters. So to solve this, we know that from Breath-Batho equation of closed sections. So this is valid for closed sections. So the torque T can be written as 2AQ, where Q is the shear flow. So this can be again written as 2A into tau into T. So where tau is the shear stress. So they are also saying in the question the shear based on the maximum stress criterion, you can say the ultimate stress is equal to the shear stress that is applied on the wall of the tube. Okay, so that is equal to 2 into the area of the tube will be pi into Rm square. Since they are giving you the mean radius, you just take it. If they are not giving you, they have to take the mid dimensions when you are calculating for torque or shear flow or shear center. You should always take the mean dimensions. or the mid dimensions in aircraft structures. Tau into T, that is equal to 2 into pi. Just substitute the values into 0.2 whole square into, and the shear stress they are giving 200 into 10 to the power 6, since they are giving in megapascal, and the radius of the tube is 0.004 meters. Now by solving this, you will get torque T is equal to, since they are asking in kilonewton, you just take the 10 to the power 3 outside, so you will get it around 201 kilonewton meter. Let's solve question number 33. The response x of t of a freely vibrating single degree of freedom under damped system is given below. In the equation, a and phi are constants. The damping ratio of the system is dash, and they are asking round off to 3 decimal places. Let's see how to solve this. Since they are giving you the response of the system, let's see, we can compare this. Since it is under damped system, if you know the response of under damped system, x of t is equal to some constant. Let's say, since they are taking a, so I'll go with a. So a into e to the power minus zeta omega n t into sine omega d into t plus phi. So this is the response of an under damped system. So now you can compare this zeta omega n with, comparing these two, you can write zeta omega n is equal to 5 and omega d is equal to 10, where omega n is the natural frequency of the system and omega d is the damped natural frequency of the system. Now if you write zeta into omega n, that is equal to 5, and omega d is equal to 10. Now from here, omega d can be written as omega n into square root of 1 minus zeta square, that is equal to 10. Now just substitute from here, you can write omega n is equal to 5 upon zeta. Take this and substitute here. So this will be 5 divided by zeta into square root of 1 minus zeta square, that is equal to 2. Now you cancel on both, 5 1s 5 2s. So this will give us square root of 1 minus zeta square upon zeta, that is equal to 2. Now by doing squaring on both sides, we will get 1 minus zeta square divided by zeta square, that is equal to 4. Then 1 upon zeta square minus 1 is equal to 4. Then 1 upon zeta square will give you 5. Then from here, now you take the square root on the right hand side. So you get square root of 0.2, that will be 0.447. Since they are asking up to 3 decimal places, so the answer to this is 0.447. Let's do question number 59 from mechanical vibrations. A system comprising a bar, spring and mass is shown in the figure below. The bar having negligible mass is made of a material having Young's modulus E is equal to 200 gigapascal. Cross sectional area is given 100 millimeter square and length 100 millimeter. The spring stiffness K is given as 200 kilonewton per millimeter and the mass 100 kg. The natural frequency of free vibration of the system is dash radian per second. Round off to nearest integer. Let's see how to solve this question. So first thing is, we should know how to convert this bar into a spring. Okay, for that we know that stiffness of the bar is equal to EA by L. So that is equal to 200 into 10 to the power 3. So try to write the Young's modulus in millimeters square into area of this is 100 divided by 100. Cancel these two. We'll get it as 200 kilonewton per millimeter. So once you attain the stiffness of the bar, now these two are connected in series. So two springs. So this is the stiffness of the bar. You can call this as K1, and this is the stiffness of the spring, and you can call this as K2. And K2 spring stiffness is given around 200 kilonewton per millimeter. From here you can conclude that K1 is equal to K2, that is equal to K. So both are having the same stiffness. So since these two are connected in series, we know that for series connection 1 by K equivalent is equal to 1 by K1 plus 1 by K2. So from here you can write K equivalent is equal to K1 K2 divided by K1 plus K2. So this turns out to be, since both are having the same stiffness, so this will be K square upon 2K, this will be K by 2. Okay, so this is the equivalent stiffness of the system. So to find the natural frequency of a spring mass system, we know that omega n is equal to square root of K equivalent divided by the mass of the system. So since you have the K equivalent, now substitute here, that will be K by 2m, that is equal to, since K is known to you, so that is 200 into 10 cube divided by 2 into, so the mass of the system is 100 kg. Now you see here, this is kilonewton, kilo I already wrote, then Newton per millimeter. So Newton can be written as kg meter per second square. Since you have 1 meter there, you try to convert that to millimeter. So into 10 cube you do. So you should be very careful here with the units. Then this will come out to be, so it is under root 10 power 6, then it will be 1000 radian per second. Let's solve question number 45. The deformation of an open section bar subjected to pure torsion can be solved by choosing an appropriate Prandtl stress function. Which one of the following statements is true about the Prandtl stress function? Let's see how to solve this. So you have 4 options. It satisfies equilibrium equation. It is 0 on the lateral surfaces of the bar. The third option, it satisfies compatibility equation, and the fourth one is it does not satisfy the equilibrium equation. So to solve this, first you should have the basic knowledge on the Prandtl stress function. So Prandtl stress function, it is denoted by phi. So you can write tau xz is equal to dou phi by dou y, and tau yz is equal to minus dou phi by dou x. Now to check the first option, we know that from equilibrium equation, you can write dou tau xz by dou x plus dou tau yz by dou y, that is equal to 0 without body forces. Okay, then if you try to substitute the above two expressions in the equilibrium equation, dou by dou x of dou phi by dou y plus dou by dou y of minus dou phi by dou x, that is equal to 0. Now you can see from this equation, it's satisfying the equilibrium. Okay, this will turn out to be dou square phi by dou x dou y minus dou square phi by dou y dou x. So it satisfies the equilibrium. Now first option is correct. Now if you see the fourth option, it does not satisfy the equilibrium equation. Now you can eliminate this directly. Now to check for these two, it is 0 on the lateral surfaces of the bar. Okay, so we know that from open section torsion, you can write dou phi by dou s is equal to 0, where s is the tangential direction of a open section. So it is along the tangential part, and this is the thickness T, and you can call this as B. This is the length of it, and this is the thickness of open rectangular section. Okay, so on the surfaces of the bar, I mean the lateral surface of the bar, it is 0 because it has to satisfy this for thin walled open section beams. Okay, now this is correct, option B. Then if you go for option C, it satisfies the compatibility equation. So for that you need to write the compatibility equation for Prandtl stress function. So for option C, compatibility equation is del square phi is equal to minus 2g theta. Prandtl stress function can be used to solve the non-circular cross sections to calculate the torsion in aircraft structures. So this equation can be used to solve any kind of cross section to get the torsion and torsion constant. So obviously if you see this phi here, it has to satisfy the compatibility, since it is satisfying the equilibrium equation. Okay, this phi can satisfy the compatibility equation also. So option C is also correct. Then option D is wrong. Correct answers are A, B and C.